Hello, everyone. Welcome. Thank you so much for joining. We'll be starting in just a minute. All right, it's 101. Hello and welcome to today's Better Buildings, Building Operations During COVID-19 webinar. In this series, Better Buildings, DOE laboratory scientists and leading professionals will be providing updates on relevant research and technology, addressing frequently asked questions by building operators, identifying opportunities to enhance energy efficiency, and discussing lessons learned from the pandemic to build resiliency. Next slide. I'm your moderator, Mariana Ejea Casal-Duke. I'm an ORISE Science, Technology, and Policy Fellow with the Commercial Buildings Integration Team within the Building Technologies Office. The Building Technologies Office is then within the Energy Efficiency and Renewable Energy Office of the U.S. Department of Energy. I work primarily on better buildings and serve as the healthcare and hospitality sector lead. So happy to be with you all today. Next slide. Awesome. Again, thank you all for joining us. We have a very interesting session today, but before we dive in and I introduce our speaker, I'd like to go over some brief housekeeping items. First, I'd like to remind you all that you are on a muted line. All questions for our speaker will go through Slido, and I will walk you all through how to use Slido in just a moment. If you have any trouble with GoToWebinar, or experience any other audio or visual issues, please chat our technical support using the chat function. Please note today's session is being recorded and will be made available on the Better Building Solutions Center. Next slide. Like I just mentioned, we will be using Slido for Q&A. Please go to www.slido using your mobile device or open a new window in your internet browser. Today's event code is #DOE. If you'd like to ask our panelists any questions, please submit them at any time throughout the presentation using Slido, and we will be answering your questions near the end of the session. You can select a thumbs up icon for questions that you like, which will result in the most popular questions moving to the top of the queue. Now, let's move into the presentation portion of today's session. So I'd like to introduce Marcus Bianchi, Senior Research Engineer at the National Renewable Energy Laboratory. Marcus is going to briefly introduce the Space Conditioning Technology Research Team. Marcus?
Yes, good morning, good afternoon, depending on where you are. The Better Buildings Alliance HVAC Technology Research Team at NREL is 3 of us. You know, it's Marcus, myself, Greg Shukas, and Michael DeRue. We support all the space conditioning work under Better Buildings and perform, research supporting like the Better Buildings goals. Next, please. Some of the highlights of the work that we do in the space conditioning team, we collect the information in the HVAC resource map. The address is on the screen now. If you look at it, you can actually follow different aspects of space conditioning to consider. So, please visit. If you have any questions, please forward us a message about it. That's about it. Thank you so much, Mariana.
Thanks for joining us, Marcus.
Mariana, you seem to be muted.
Wonderful, thank you. Now I'm very happy to introduce today's presenter, Dr. Jason Degraw. Dr. Jason Degraw holds a BS in Mechanical Engineering from the University of Houston and an MS and PhD degrees in Mechanical Engineering from the Pennsylvania State University. He is the program manager for the Weatherization and Intergovernmentals program and a member of the R&D staff at Oak Ridge National Laboratory. Dr. Degraw's research work has focused on numerical simulation of thermofluid flow phenomena at a variety of scales and in several different application areas. His recent work in building performance simulation has applications in indoor air quality, building security, and resilience. Dr. Degraw is currently a member of the Energy Plus development team at US DOE's flagship building energy simulation engine. As a reminder, please send any questions for Dr. Degraw through Slido by going to slido.com and typing in the event code #DOE, and we'll try to get as many of those as we can at the end of Dr. Degraw's presentation. Thank you for joining us, and please take it away.
Thank you very much. All right, so I want to talk to you today about some of the work we've been doing at Oak Ridge, specifically on office buildings and ventilation, how COVID-19 and other pathogens spread between zones. This was work that I've done in collaboration with a postdoc here at Oak Ridge, Pratik Srestha, whose name I still can't quite get right even after a couple of years. Next slide, please. I think we can skip this one, go on to the next slide, go right to the outline. I want to talk about some background sort of material first, then talk about specifically about multi-zone transmission and ways we can look at that and study that. Then briefly touch on the energy impacts, then talk about some things that were proposed by ASHRAE as the core recommendations, part of the epidemic task force. I've been part of that since March or so of 2020. And then we'll move on to some conclusions. Next slide, please. So it's always good to think about, why we're here. And fundamentally, we should think about why do we do HVAC, heating, ventilation, and air conditioning. Sometimes you tend to get sort of lost in using the acronym HVAC and not really think about what those words actually mean. Fundamentally, we do HVAC because we have to. Here in Tennessee, where I live, if there wasn't air conditioning, it would be pretty unbearable to be in most buildings. It gets pretty hot here and humid, so we need the ventilation and air conditioning in order to keep spaces habitable. We are fundamentally trying to maintain acceptable indoor environmental quality, which we'll talk about here in a few slides and what that really means. But it's not really aspirational or inspirational. We're not trying to keep people healthy. We're just trying to keep conditions acceptable, whatever that means. Next slide, please. So before we talk about what acceptable means, let's talk about what indoor environmental quality means. One sort of typical way to look at it is a combination of 4 factors: the indoor air, the quality of the indoor air, the quality of the lighting, the quality of the acoustics, and the quality of the thermal conditions. And this is all very subjective. Things that may bother me may not bother you, and vice versa. And some of that is determined by climate, cultural factors, how a building is used, how the occupants behave, what the occupants are doing. There's a lot of things that go into thinking about what indoor environmental quality means, but it is still very subjective. What's good for me may not be good for you, and that makes it somewhat difficult to talk about indoor environmental quality in very general terms. Next slide, please. Even so, we spend a lot of money on maintaining indoor environmental quality. This data is a little bit old, but it's projection for 2025. And if you look at space heating, space cooling, lighting, and then ventilation there on the other side of the pie chart, that adds up to nearly half of what is used in energy for buildings. If you just look at if you drop out lighting, you're still over a third, and you're still spending a lot of energy and ultimately money on maintaining acceptable indoor environmental quality. Next slide, please. So the connection today to energy is really going to be through IAQ. What is IAQ? Indoor air quality is defined by EPA as the quality within and around buildings and structures, especially as it relates to the health and comfort of building occupants. Poor IAQ is often associated with uncomfortable humidity, uncomfortable smells, things like that. If you've ever been in a space that smells bad, or the humidity is not quite right, you know that it can be very difficult to stay in those spaces. The relevant ASHRAE standards here are 62.1 and 62.2, which set the acceptable standards. So 62.1 sets acceptable standards for commercial buildings, which is more of interest today, and 62.2 is for residential buildings. Next slide, please. So what do we mean when we talk about acceptable IAQ? Well, fundamentally, acceptable IAQ is about controlling contaminants. Now, what's a contaminant and what's not a contaminant can be a little controversial, especially when you start talking about carbon dioxide, but the easy ones are things like dust or smoke, VOCs, so formaldehyde, et cetera, coming off of furniture typically, radon coming out of the ground, and then pathogens that we as occupants may introduce, so bacteria and viruses and other similar things. Control measures include ventilation, which we're going to talk a lot about today, and air cleaning, so filtration, et cetera. One of my colleagues has a cat who very much likes to filter the air that enters his space by sitting on the register here. I think this is funny. I guess not everybody thinks it's funny, but especially if you're allergic to cats, this might not be the best way to condition a space. Acceptable, I want to point out here, is not the same thing as healthy. And one of the things that has sort of through this pandemic become more of a topic of conversation is how we have focused for many years on this idea of maintaining acceptable IAQ, but we haven't necessarily thought how that relates to healthy IAQ in a more broad sense. Next slide, please. So IAQ is the factor of IEQ that connects HVAC to the management of pathogens. Now, when I say ventilation during this talk, I'm talking about the introduction of outdoor air, or in this case, hopefully clean air into a space. Proper ventilation has shown to be an important defense against COVID-19. We have other ways of getting at that, mask wearing, social distancing, other things like that. But there are a few things that have proved to be more effective than properly ventilating a space. Now, we can do air cleaning and similar things to sort of do the equivalent of ventilation, but as of right now, we really have not found a better approach to protecting ourselves against the virus that transmits COVID-19. To a certain extent, some places it feels like the pandemic is over now. Here in Tennessee, we are rather having some trouble with vaccinations, but we do need to recognize that from a scientific standpoint, we're at the point that we need to be talking about what it means to be prepared for the next pandemic. Hopefully there won't be another one of these, but if you think back, you don't have to go too far back to talk about Ebola and what was that, 2008, 9, 10 timeframe, and then you can go back to the SARS outbreak in Asia in the early 2000s. I hope that the experience in this pandemic has changed how people approach some of these things. But from the scientific side, from the buildings research side, I don't think we can afford to take a chance there. We need to, as a researcher, I need to be working hard to make sure that everyone understands what the things we should learn. So next slide, please. Partly why we need to probably be thinking about the next pandemic is that there is a lot that we still don't know about SARS-CoV-2, the virus that causes COVID-19. We do know a lot about it. Here's a picture from the CDC. We know that the virus is about 0.1 micron in diameter. We know the droplets that are important here, so it's that we can do experimental studies to determine how the particle size distribution of coughing or sneezing or similar activities that produce the sorts of particles droplets that contain the virus. We understand the basic physics of how particles move around in the indoor environment, and we do have some idea of what it takes to become infected. if you're familiar with the Wells-Riley equation, there's a parameter in there called the infectious quanta, and there have been a number of estimates of that quantity. Now, unfortunately, there's a pretty big plus or minus window on those numbers right now, but I would expect that as time goes on, we'll get closer and closer. But we still don't know really what the production rate is. So if I was infected, I don't really know how much virus I'm producing. I know, like I said, I know something about the droplets of moisture that I'm producing, but I don't know how much virus is really in those. We don't know how much it really takes to be infected, the so-called infectious dose, which is related to this infectious quanta, but not quite the same thing. So we have a lot that we still need to learn. And excuse me, in the indoor environment, there's a lot going on in indoor environments. Next slide, please. Where we have to be concerned about the droplets and particles that infected individuals are producing. We know somewhat what will happen with those as you encounter them. For bigger droplets or particles, 5 to 10 micron or so, that's likely to be caught in your upper respiratory system, in the mucus there doing its job to protect you, and they don't make it down into the alveoli where they can actually infect you. If particles or droplets are very small, say less than 0.5 micron or so, they are very likely to actually breathe back out. So you breathe them in, they can go all the way down to the alveoli level, but they can be exhaled rather than actually making it to the bloodstream. It's a sort of around the 1 micron range that you have to worry about. And unfortunately, if you cough or sneeze, you do produce a fair amount of those. So when we're talking about how the COVID-19 disease is transmitted around, it sort of works its way back to what are we doing to address these particles and droplets that are being produced. So next slide, please. So we're here today to mainly talk about office buildings, and that really means multi-zone transmission. Some background and assumptions here. Office buildings, at least here in the United States, are conditioned by large central systems, whether they're rooftop units or bigger boxes contained elsewhere. Multiple zones within a building will typically share the same air handling system, so they're multi-zone, and that's where some cause for concern because of the shared air, as it were. And then finally, systems will be assumed to be working properly unless otherwise noted. I do have a slide later where we'll talk a little bit more about this, that maybe this is not the greatest assumption, but at least to start with, let's assume everything is working properly. Next slide, please. So does multi-zone air distribution increase risk? So do multiple zones sharing single air handling systems increase risk? Well, the simplest answer is yes, but next slide, please. My low budget animation here of overlaying slides. And no, there is more to the story than just a yes or a no can convey. Yes, risk is increased, but not all risk for everybody. Let's talk about a case here that we'll make a little more detailed in a moment, but let's talk about a medium-sized 3-story office building. We'll give each floor its own air handling system with a plenum return strategy. We'll have an infected person in one zone in that building, and then we're going to assume we got roughly 30 similarly sized zones. So the volume of a story is approximately 10 zones. So next slide, please. So the easy answer, yes, risk is increased. Well, zones without a pathogen source would have no pathogens without this shared air. So the way that the pathogen is getting to this new zone is it starts out in the zone where there's the infected person. It's then pulled up into the system. It travels through the system, is redistributed out to the zones. And now look, here is a zone that would not have had pathogen in it except for this multi-zone air distribution. now has some pathogen in it. So obviously there's more exposure of the occupants. Once you're exposed to something, then you can catch something. So increased exposure means increased risk. So the simplest answer is, well, yes. Next slide, please. But if you think harder about it, no, risk is also decreased, for at least for some. When you spread the pathogen around the whole building, like we're doing, even if you just confine yourself to the zones that are shared, you reduce the concentration that is experienced by the people in the zone of release. So if you just want to think a very simple approach to it, the concentration is going to be the mass of pathogen over the volume of the whole story now, instead of just the single zone where you were. And because of our earlier assumption, that works out to be an order of magnitude decrease in that the source zone. Increasing ventilation and filtration actually further reduces exposure in the source zone. So at least as far as the source zone is concerned, there is a reduced exposure, which means reduced risk. So it isn't possible to really say yes or no for this. It is really somewhere in between. As we have found so go ahead, next slide, please. Sorry, I'm talking ahead of my own slides. What has happened in this pandemic is that we have not found, that I am aware of, any cases where it has been demonstrated that there was transmission of COVID-19 through a multi-zone air distribution situation. That doesn't mean that the virus isn't traveling through, and pretty much you should assume that there's viral material everywhere, because all of the studies that I have seen indicate that pretty much the virus is going everywhere. There is, however, some evidence of transmission through plumbing systems. So some sort of gross shared plumbing situations, you end up with transmission that appears to be through the plumbing system. So even though there's no evidence now, it could happen. And we also, as I said earlier, need to be thinking about the next pandemic. What does it mean for the future? It is entirely possible that in the future we will encounter a virus that does survive the trip through HVAC systems and would be much more dangerous. Next slide, please. So those of you familiar with the DOE prototype buildings may have sort of recognized my bullets earlier as sounding suspiciously like the medium office prototype building. Well, the reason they sound suspiciously like that is that for our computational studies, we actually used a CONTAM version of these Energy Plus prototype building models. So a little more detail there. This is a slightly modified form of the medium office prototype. If you're familiar with these, the traditional medium office prototype has a 5-zone perimeter core zoning setup, and this one has been subdivided to be more detailed and be a little bit more zoned, a little bit more exactly like a real model would look. Actually, if you look really carefully at that graphic there that's labeled Open Studio model, I think that picture is actually from the traditional one and not from our subdivided one here. But this is the model that we were doing testing in. Again, plenum return, 3 stories. There's 2 stairwells and 3 air handling units, and then 1 exhaust fan per bathroom. Next slide, please. What we did was we developed airflow models based off of this model. I'm using NIST CONTAM software. Looks like I have a botched middle bullet there, but the building representation is created very much like what you do for an energy model. You take the building characteristics, the HVAC details, you create a representation that CONTAM can understand, just like you would with energy modeling software, and then you're able to compute movements of air and contaminants based upon those inputs. Now here's it's a little hard to see because it's a little small, but there's the bottom level there at the bottom is how that looks. Each one of the plenums looks exactly like that middle plenum picture, and then the middle and top level look like the depiction there at the upper right. Next slide, please. So what we did was we placed, I'll show you just one example here, and this is, we go into more detail on this in the couple of conference papers that we published and working on publishing a journal paper right now. We have the star marks the source, so there's the index patient or index person. They're in the third level in sort of a lobby area. The colors you see are the concentrations of the contaminants, and then there's 3 columns there. The left-hand column is 0% OA, so 100% recirculation, and then a more reasonable OA level, 30%, 31%, maybe still a little high, and then a 100% OA situation in which we recirculate nothing, and all of the air that's distributed to the zones is outdoor air. So when you're recirculating everything, you get fairly high concentrations throughout the building, even though the excuse me, the levels 1 and level 2 do not share the same HVAC system. They are connected via shafts and other penetrations, so you get fairly effective distribution of the contaminant throughout the building when you're at complete recirculation. You recirculate less, and you do find quite a significant drop off. As you can see there, it goes from the highest values on the 3rd floor down to the middle values there on the 2nd floor, and then down to much lower values on the 1st floor. If you do 100% OA, you very effectively prevent that sort of distribution. So you get no contaminant concentration on the 1st and 2nd floors, and you get only a very minor spread there on the 3rd floor, where the interzonal connection, so open doors, et cetera, things like that, will allow for a spread of contaminant, even though you're still doing at 100% OA. Next slide, please. So I've used the word exposure a number of times, but for the purposes of post-processing our results, we need to be a little more particular about what we mean. So exposure, if you look up at the sort of dictionary definition, it's the state of being in contact with a pathogen. In terms of how we actually quantify that, the quantity of the exposure is what we're calling the exposure dose, which is the product of the concentration and the time. If your concentration is constant through time, you can just multiply the concentration times the time, or if you've got a time varying concentration, you actually need to do an integral to get to the same thing. Higher value means more impact. Now, what we can't say, because we don't know what the infectious dose is for COVID-19, we can't connect this to an actual outcome. So all we can really say here is something relative, that one situation is better than another. We can't say, for instance, that 5 or 10 people or 15 or 20 people are infected. We can't get to that because we don't have the infectious dose. Now, we could follow a Wells-Riley approach, and you'll see a lot of that in the literature where you can get to something similar to that, but fundamentally, we're still almost always going to be talking about sort of relative exposure impacts as the assessment, rather than a specific number of infected people. In cases where you do know the infectious dose, if you do know how the disease is transmitted, say with anthrax or something similar, you can actually get to sort of these actual mortality type outcomes, but that's not really possible in this case. The next slide, please. What we've done is we've come up with a way to relate the exposure and the floor area. So you want this graph I'm showing here at the right is another representation of the results I showed you earlier. The way you want to think about this is we've divided the area up into 10 bins. So each one of those bins that were labeled as cumulative area deciles are 10% of the area, and the exposure dose there is actually a normalized exposure dose. The conference paper and the upcoming paper will have more detail, but I don't want to spend a whole lot of time on this. The way to understand this is higher values mean more of an impact. So if you look at the yellowish, sorry about the colors here, I did not choose wisely. The yellowish bars reflect the results for the 0% OA case. And if you recall, that spread the contaminant around pretty effectively. And so you see a fairly flat trend there across much of the building where you do not, there is some drop off from the release zone, which is always going to be to the right here over in the top 10% of exposed area. And that's just to be expected. The source zone always sees the highest impact. What you don't really want to see is you don't want to see it being spread around so much. And this case here with going to 30% OA, 50% OA, and then 100% OA, is you can see that the 100% OA pretty much effectively wipes out any spread. So you have very little outside of that top 10%, and then pretty much zero across the board there. And as you decrease your OA, you get more and more spread. And this is why, to a certain extent, ventilation is really one of the most effective weapons we have here, because there's not really a way to do this without doing introduction of essentially clean air. Now, the counter argument here, which I think I'll come back to a bit later, is that you do have a bit of a problem if your outdoor air is not as clean. So if there's a wildfire going on, if you've got pollution problems, then you may not have the ability to just dump clean air into your system and into your building. So even though this does demonstrate that ventilation is the way to go here, there's still this complication that if you don't have clean outdoor conditions, you've got a problem. Next slide, please. Now, one of the things that has come up during this pandemic and actually previously in security type situations is the suggestion that ducted return may do better. So instead of having a plenum return where air from all the zones is sucked up into a plenum, a common shared plenum, and then into the system, you actually duct everything so the air is carried via a duct from your return grill all the way back to the system. And it does make some logical sense if you think about it, because ducts contain the pathogen better. So you'd say, well, okay, if I want to contain the pathogen, well, then I should use ducts. But the unfortunate side effect of using ducts is you have less of a volume involved. Next slide, please. This is the situation for this particular building. Again, showing 0%, 31%, 50%, 100% OA. In some cases, yes, it does slightly better. But what we actually find for this building is that it short circuits return a bit, and it means that the contaminant arrives back at the air handling system sort of quicker than it would if it was using plenum returns. So you actually are getting an enhanced spread in some cases. And you can see that at the higher OA cases here, where you're getting spread that's not necessarily working as we would have expected. Okay, next slide, please. So again, to come back to my earlier slide, the title at least, details matter. Ventilation is still the #1 countermeasure that we have, but there are other strategies that may work in conjunction, with ventilation, including filtration, air cleaning, etc. But the building specific details really do matter. So the height of your building, the number of vertical shafts, environmental conditions, all those things really matter. And that's what makes it so difficult to make sort of general pronouncements about something like this. Again, to go back to this idea of saying, oh, well, just go 100% OA. Well, that's only possible if you've got clean outdoor air conditions. If you're in a situation where the outdoor conditions are not great, you are not able to just bring in outdoor air with no penalty there. This is, you know, to get back to the wildfire situation, as there have been more and more situations where wildfires have been a problem. Outdoor air is maybe less accessible these days. And what we're going to do, what we need to think of this, I think, really is that there are going to be multiple strategies, and you're going to have to think about it in terms of a particular building. You can't think about it, well, you know, this solution will work for all buildings. It matters what the building is, what it's used for, and where it is. And I think the next slide, please. One of the things that was done recently that will hopefully give us a little more insight here is, next slide, please. NREL did some Comstock analysis. I believe they actually did a webinar on this, so I believe that would have been recorded. So I encourage you to go back and take a look at their webinar. What they did was they used their platform to look at some of the measures, like some similar to what we've been talking about. The measures that they did are maybe a little outdated now because, you know, they started their analysis some time ago, and, you know, it's not easy to get these simulations completed. So what we may be recommending now, and we'll spend a little bit of time at the end of the presentation going over some of the ASHRAE recommendations, or what the recommendations are now. There's still good news and bad news to be had from the work that NREL did. Next slide, please. Here's the energy use intensity by climate zone. And mainly thing I want to point out is each one of those, there's sort of a one sticking up, especially once you start to get past, you know, 3A or so, it really starts to get pronounced there. And that's unfortunately the highest OA. Next slide, please. That's the energy use intensity divided by that's the energy use divided by the area. Here's the total energy consumption by climate zone, same thing. And you'll see again that there's in most of them, there's one sticking out, and that's the one that is the most OA intensive. So next slide, please. I just spent all this time telling you that, you know, ventilation is the way to go. And it's great that the filter upgrade does not seem to have a significant energy cost, and flushing is not as bad as it could be. The bad news is the increased outdoor air is pretty costly. And even that flushing case is not as good as we would like. So there is an opportunity here. I'm not going to spend a lot of time talking about it in this presentation, but I do believe that there is really, you know, as engineers, we have an opportunity here to innovate. Particularly based upon the recommendations that we'll talk about here in a moment, we have some work to do in terms of fixing the situation. So next slide, please. Next slide, please. Just get into talking specifically about this. Early on in the pandemic, it was easy to understand why, you know, HVAC professionals were very worried. You know, is HVAC part of the problem? A lot of people were asking that question. Are HVAC systems making this worse? Is multi-zone air distribution a nightmare that we have to stop immediately? ASHRAE and other similar professional societies started getting questions from membership. And the next slide, please. ASHRAE's response was to put together an epidemic task force that I am a member of. I'm actually the transportation lead. Next slide, please. The outcome of all that was guidance. So there's several hundred pages worth of guidance available on the ASHRAE webpage. So that includes a lot of building type specific stuff, frequently asked questions, and there's a lot of work been done recently on reopening guidance. Next slide, please. One of the things that started to happen after we put out all that guidance was we started to get a lot of questions about why recommend this, why recommend that. And we realized that a lot of the guidance shared sort of common core ideas, and we decided to break that out as a separate document in order to provide an entry point for the guidance, provide something at a higher level that people could sort of dive into and understand better without having to get into a lot of the building specific details. Next slide, please. And we came up with basically 5 points of core recommendations. Not all of those are directly applicable to our topic today, so I'm just going to talk about 3 of the 5, the ones in bold there: the ventilation, filtration, and air cleaning recommendations, the air distribution recommendations, and then the system commissioning recommendations. So next slide, please. So under ventilation, filtration, and air cleaning, we asked that to provide and maintain at least required minimum outdoor airflow rates for ventilation as specified by applicable codes and standards. This is really talking about our understanding that right now our most effective approach to mitigating these impacts is to ventilate. So you should ventilate first and consider other measures later, is the recommendation from ASHRAE. Again, dilution of the pathogens is an effective approach. Our modeling shows that. The outcomes that are documented in the literature document that. And you really need to think about ventilation first, other measures second. Next slide, please. Also under that same heading, ASHRAE recommends using combinations of filters and air cleaners that achieve MERV 13 or better levels of performance for air recirculated by HVAC systems. So MERV 13 has a pretty good efficiency against the biologically generated aerosols that we're talking about. So the particles and droplets that are produced by sneezes and coughs, that sort of stuff, MERV 13 is pretty effective against. Again, we're not so worried about a single virus. I don't think anybody's expecting the infectious dose to be 1. This recommendation does allow for trade-offs, so you can start to think about how do we engineer something here? How do we achieve MERV 13 levels of performance or better without actually applying MERV 13 filters? The filtration that NRL studied in their Comstock runs didn't have much of an energy penalty. So certainly if that's something that can be applied, that's great. But the fact is that many situations you wouldn't be able to increase the fan pressure drop sort of things, and you would run into problems. If you've ever had a coil freeze on a residential system like I have in the past, when it decides to actually melt, then you've got a real problem. And increasing your filtration has the potential for slowing down airflow, and that's when you get things like coils freezing. Next slide, please. So final discussion point here under ventilation, filtration, and air cleaning is select control options, including standalone filters and air cleaners that provide desired exposure reduction while minimizing associated energy penalties. So again, while we're still aiming to do as much ventilation as possible, this is allowing for control selections in particular that can meet an overall target. And also, even though I don't particularly like, the mathematician in me doesn't like the use of minimization here, the overall point is that energy use can be considered. So while we want you, the ASHRAE ETF wants you to get to those targets, we're not demanding that you get there irrespective of the energy penalties. Next slide, please. So one item here on air distribution, and it is where directional airflow is not specifically required or not recommended as the result of a risk assessment, promote mixing of space air without causing strong air currents that increase direct transmission from person to person. I've spent a bunch of time here telling you that ventilation is important, and that in this pandemic, there isn't much evidence that there's transmission outside of the source zone, so that there's little risk associated with multi-zone air distribution. That does not mean that there aren't risks associated with your air distribution strategy. There's a famous case here from South Korea where you can actually draw a line between the infected parties. Depends how I think you can kind of see that there. The overlap between one of the people that was infected and the source was only 5 minutes. So what was happening here is that the way that the air was being distributed within this zone was creating this air current that tended to carry air across these people, and infections resulted. Mixing, again, tends to reduce the concentration of the pathogen at any particular point. So the more mixing there is, the lower value of the concentration you'll be encountering, and that means your exposure dose is lower, to refer back to that. Next slide, please. The last recommendation I want to talk about today from ASHRAE is that verify that HVAC systems are functioning as designed. The guidance doesn't make a whole lot of sense, and none of these recommendations make very much sense if the systems aren't working as they're supposed to be working. And unfortunately, there are a lot of systems out there that aren't working like we think they're working. I encountered a situation in a demonstration project some years ago where a fan was installed backwards, which you would think someone would notice, but it wasn't noticed. There's this GAO report here that there's a link to there, and I would encourage you all to actually take a look at that. The presentation is a little bit complicated to parse, but the figure shows the estimated percentage of school districts in which at least half of the schools need updates or replacements of key building systems or features. So half of the buildings need updates or replacements. That top item, which you may or may not be able to see, it's a little blurry on my screen, is heating, ventilation, and air conditioning systems. And that is marked out as a 40.9 is their average number, and it looks like they've got, maybe, it's hard to tell here from this picture, but you know, a couple of percentage points either way, 5 to 10. So there's a pretty big bound on that. Either way, any number in that range is horrifying. That many potentially school buildings in the United States could need significant work is and should be horrifying to pretty much everybody, because if systems are not functioning properly, all of this guidance is not all that helpful, because if the system doesn't work, you don't really know what it's doing. If you look at some of the famous cases of COVID transmission, the ASHRAE virtual meeting last year, Hugo Lee presented on their work relative to this transmission case with a bus. They found the bus, they had the actual bus, but they found that its air conditioning systems were so totally broken that they had to actually find they had to actually bring on to the project people who understood how the system was supposed to work, so they could figure out how it was working, so because it was completely broken. Maintenance is a known issue, and it's something that I hope that we'll learn from this pandemic, is that we shouldn't take for granted that systems are working. We shouldn't take for granted that there's not going to be any impact from that. And it's an important part of the ASHRAE recommendations to actually make sure your systems are working properly. All right, next slide, please. Down here to the end, just got some conclusion slide to go through, I think, here, and then we're done. Next slide, please. Okay. So to reiterate the top level point, multi-zone transmission has not been demonstrated to be a factor in the COVID-19 pandemic, but that's no guarantees for next time. Building specific details, that means geometry, climate, maintenance, all those things are very important. We can't drop the ball on any one of those and expect a good outcome. Research continues to point to ventilation as the primary countermeasure. But as we've noted and has been shown within real simulations, ventilation is expensive. There's a lot of work to do, but hopefully there's a better understanding of that building to health relationship now. One of the things that I didn't know I was going to know about my house, was that I was going to be intimately knowledgeable about whether or not the air distribution is working properly or not, because I wasn't really planning on spending so much time in my house. But I've been, like a lot of other people, been working out of my home for over a year. So even as a researcher in this area, I feel like I have a better understanding of that, and I hope other people are getting that too. Next slide, please. Just have some references here. There's the 2 conference papers are there, and as I said, we have a journal paper in development. And then there's all that you could ever want to learn about air return strategy and indoor air quality is covered in that NCMBT report. Next slide, please. All right, thank you very much for your attention. I appreciate everybody's time. Please fire away with questions, and you can always contact me directly there at my email address.
Awesome. Thanks, Dr. Degraw. Wonderful. So it's time to move over to Slido, and we can see what folks have been asking us. Got it. First question from Anonymous. Is there a conference paper available for public? Is there a reference? I assume they might be referring to the CONTAM model.
Yeah, so there's 2. There was in that references slide. Both of those are out there now, and we do have a journal paper that includes content from both of those that's in submission right now, I believe.
Great. And then I just want to remind everyone, once the slides are uploaded to the Solutions Center, all of the links that are available throughout the slide, you'll be able to activate those and use those. Great. And then next question by Baburaj. If you have any questions about technologies that were not discussed during this presentation, you can please feel free to email me. My contact information is going to be available in the next slide once we're closing out the session.
Yeah, so there have been a couple of DOE projects on air cleaning. There's the HVAC load reduction report that I was involved in while I was at NREL. So yes, there is a lot of interest in air cleaning. One of my old colleagues at NREL would always say I'm more interested, Eric Kozabal would always say he was more interested in making ventilation cheaper than trying to scrub air. So it's all a very active area of research and development.
Awesome. One more question. Is it useful to install UVC lights inside HVAC ducting?
So UVGI, or ultraviolet germicidal irradiation, is a technology that ASHRAE has recognized as effective against pathogens like SARS-CoV-2. So yes, but it's not something that should be undertaken without expertise, because the UVC lights are dangerous. They're not, electrocute you dangerous necessarily, but they can give your eyes a very bad sunburn. And so it's not something that should be done without the appropriate expertise.
Wonderful. Thanks, Dr. Degraw. I think those are all of the questions that we have as of right now. I'm going to give it a few more seconds just in case anybody wants to write in a last-minute question. You can go to www.slido.com and use the code #DOE to ask Dr. Degraw a question about his presentation. All right, I think we can move forward. So as I mentioned, the recording and the slides will be made available in the Solutions Center. If you would like to take a deeper dive into today's topics, I very much encourage you to visit the resources that are listed on this slide once the slide deck is available. Next slide. The Building Operations During COVID-19 webinar series will be going on a hiatus after this installment. However, we will be including related content in our upcoming 2021-2022 annual Better Buildings webinar series, which will begin in September. We also have a webinar coming up tomorrow on a similar topic, workplace evolution, supporting occupant health while achieving energy efficiency. This webinar is part of our summer series, and you can sign up on the Solution Center. Next slide. Great. I also encourage you to visit the Better Buildings COVID-19 Resource Center. Here you can learn from the experts with resources from ASHRAE, EPA, DOE, and more. View resources by technology type and watch webinars or register for upcoming virtual learning opportunities. Next slide. Wonderful, and here you have my contact information as well as that of Dr. Degraw and Marcus Bianchi. Thank you, Dr. Degraw, and thank you, Marcus, for being with us here today. Please feel free to contact any of us directly with any questions about your general HVAC questions, pandemic preparedness and response, and any questions that you might have about Dr. Degraw's presentation here today. I encourage you to follow Better Buildings on Twitter for all of the latest updates, and keep an eye on the Solution Center to register for webinars and virtual learning opportunities. Wonderful. Thank you, everyone.